session is a keynote address, and we have with us, and I would like to welcome Mr. Umesh, who is the Managing Director of Bosch Chassis Systems India Private Limited. He is our chairman for this session. Introducing Mr. Umesh, he is the Managing Director of Bosch Chassis Systems India Private Limited, prior to which he was the Business Head Industrial Equipment Division and Plant Manager of the Nagnapura plant. He has been a member of the Bosch family for 34 years and has experience in many departments at different plants of Bosch. His experience ranges from manufacturing, purchase, planning, service, plant maintenance, technical engineering functions, etc. Mr. Umesh has been a part of IMTMA for many years, and now he's shifted to becoming a customer of machine tools. We welcome Mr. Umesh, and I hand over the session to him.
Good morning, ladies and gentlemen. A hearty welcome from my side to this wonderful event, and it's a privilege to be part of this event. We have today a keynote address by Dr. Ravi Damodaran on innovation for manufacturing excellence. He will give you an overview on his assessment of manufacturing systems and what gaps he finds that could be addressed, and perhaps suggestions on roadmap that could be used towards excelling in manufacturing. He will also touch upon cultural reasons as to why sometimes we are not able to sustain these initiatives. And I have the privilege of introducing Dr. Ravi Damodaran. He is a profound thinker and an analyst with rich experience in manufacturing industry. He retired as President, Technology and Strategy from Varroc, where he was responsible for scripting the group's strategy to achieve its 2020 vision, as well as improving Varroc's technology prowess to achieve the sustained market leadership in its product lines. Ravi has over 25 years of experience in industrial sector, having held positions in business management, technology, program management, engineering, and operations. Prior to Varroc, Ravi worked at Delphi Automotive Systems for 10 years in various roles as Chief Engineer for Powertrain Systems and then Country Manager for Powertrain Systems business in India. Ravi spent time with GE India Technology Center for their plastics and powertrain systems. And he has spent 7 years in the United States working on advanced research in materials for space and defense applications, dental implants, cutting tools, environmental cleanups, and mineral processing. He is sought-after speaker in Indian automotive and manufacturing sector, and he hails from Indian Institute of Technology, Roorkee, in metallurgical engineering, and has masters and PhD from University of Florida, United States, and in materials. And he is married and has 2 children. So I hand over to Dr. Ravi Damodaran for an enlightening address.
Thank you.
Thank you.
A very good morning. I think it's still morning. Very good morning to all of you, and thank you for the introduction, Umesh and Gautam. I would like to focus mostly on not the innovation that we have done in our company, but the lessons learned from successes and failures in applying innovation to manufacturing. This is more relevant to us as an industry because we hear a lot of talk today about applying innovation to improve productivity and quality in our manufacturing industry. That is easier said than done. A lot of times I've been asked, okay, that is all fine, we know, but how do you do that? Because We don't have a culture of innovation in India for historical reasons. We've just opened up 20 years ago, and we are far behind some of the advanced markets by sometimes decades. How do we catch up? So I think I'll spend some time on what are things that we tried to do, what are the successes, failures. I will dwell more on failures because I firmly believe that we learn more from failures than from successes. Success sometimes gets to our head. We don't understand why we succeeded. We keep doing the same thing till we fail. If we understood why we failed, we have some nice lessons learned which we could use for improvement. That's my firm belief. So over the next maybe 20 minutes, I would give you a brief profile of the company I worked in last and the experience I've gathered. The data that I've gathered mostly are from my 25 years of manufacturing experience, 15 of them in the automotive industry. So please excuse me if there's a overindulgence in automotive examples. I will show you a little bit, glimpse of the manufacturing excellence journey we started in Varroc. Some deployment examples in various areas, including innovation in manufacturing, a little bit of, I would say, dabbling in digitization. Mostly, I would like to talk about the lessons learned, why things succeed and why things fail. We have, at Varroc, done a roadmap to achieve manufacturing excellence. I believe this has scope for improvement, but I think it's quite generic enough for all of you to start thinking of a roadmap for your own organization. And lastly, with all those experience, I have tried to make a toolkit that you can refer to while striving for excellence in manufacturing. So quickly, I'll just talk about Varroc. It has done fairly well in the last 10, 15 years. It's a 26-year-old company. It's now over 10,000 crores in revenue, over 12,000 employees, 35 manufacturing centers, almost 1,000 R&D engineers. It's a global company, but it's an Indian company. It's a privately held Indian company, so it's a success story in itself. It has two major sectors it operates in worldwide. There's one international lighting, exterior lighting sector in the automotive business, make exterior lighting systems, world-class technologies. This came as a result of a large acquisition that was done 5 years back, and we have had fairly good success in not only managing that acquisition, but also rectifying the gaps as well as growing that much more faster than the market growth anywhere in the world. The other sector is the domestic sector, which is focused mostly on two-wheeler products. These are diverse products. Varroc is, I think, the most diverse supplier of automotive components to the two-wheeler industry, which products ranging from powertrain forged machine components to lighting systems, electrical, electronics, and polymer assemblies. So it's fairly diverse. The contribution of each of the businesses are given there. It's just for information. But if you look at the growth from something like 2,500 crores about 7 years ago, they've grown to about 10,000 crores, fourfold increase, and still doing that. And so there's a secret behind that. It's called profitable growth, and the profits are managed mostly by the manufacturing organization, which is why I would like to dwell on manufacturing today. What is it that we did? So the first thing we did 5 years ago was, we were doing very well, but nobody was questioning why we are doing very well, and is there scope to improve on that? When I joined this organization with my 15 years and more experience almost entirely in world-class multinationals, I was able to see that while we are doing well in India, the processes and practices are not world-class. So it's like a lotus growing in a pond. When there's rainfall, the pond level rises and the lotus rises. Right? When the rainfall stops, the lotus dies. So I saw that risk, and we said, let's start putting a roadmap for improvements. The biggest difficulty I had was nobody believed that there's scope for improvement. We are doing so well. We are growing at 15–20% every year, and profitable growth in double-digit profits. Very rare in the automotive industry in India or worldwide. So what we did was we first convinced the business leaders to get a manufacturing assessment done. And this was done by a third party outside. I think this was Frost & Sullivan. And we looked at various systems in manufacturing which we could rate. Now, if you look at the chart above, there's areas from customer focus to supply chain to scheduling systems, asset care, that's maintenance, and various elements of manufacturing systems that needs to be there for us to get excellent. We picked up 4 of our best plants. So each one represents one division. So there's a lighting division, there's a polymer, metallic, and electrical division. Those are the first 4 in the legend up there. Then the bottommost legend, which is the blue line, is the average of the top 3 manufacturing industries in India, not just in automotive, but across all sectors. So the first eye-opener was that our best plants are somewhere 15–20% less efficient than the best Indian manufacturing companies. That was a big shocker for all of us. The second thing was there was enough variability in the systems and practices that we had. If you see, some of the plants are good in scheduling, while not good in visual management. So they're not consistent across the plants. We are following, individual practices and systems in each plant. We estimated that if we are 15–20% below Indian benchmarks, we should be about 30–40% below worldwide benchmarks. And the last thing was the manufacturing system were not documented and hence not sustainable. They were run by some competent people who one day would retire, and that would be the end of the manufacturing system, however good that would be. So these are the risks that we assessed in 2011-12. And we said that we should now get on with some improvement initiatives. So there were many initiatives. I will not name all of them, but I'll pick up mostly a few of them focused on manufacturing. And we had been doing, implementing TPM since 2008. I think most of you must have been doing the same. We didn't see much improvement. Nothing wrong with TPM. It was the way we were implementing it. And I'll talk about that in later slides. We introduced innovation in processes. So we had some fairly intense manufacturing from heavy forging to heat treatments, coatings, molding. So we had quite a few manufacturing operations. And after 20 years of being in molding business, we couldn't call ourselves an innovator in molding. We were probably the best practitioners, but we were not innovating in molding or forging. So we said we would like to now start a innovation capability focused on manufacturing processes, not on products only, but on manufacturing process. So some of the examples were, of course, it all started with automation, but that's really not innovation. That's just applying some productivity tools. But I'll probably talk about a couple of them: a deep hole drilling of engine valves, laser welding of engine valves, axial forming of transmission gears. These are new processes, and I'll talk about them in the next few slides as examples. We also had initiatives to improve enterprise systems, so connectivity, connecting our internal departments, connecting our suppliers and customers to our internal systems. Business intelligence tool to make data more visible to the management so that you could have more effective and quicker decisions. And lastly, digitization, which we are talking more often than not, almost in every conference. So, we had several dozens of initiatives and examples, but I would like to just pick up 3 of them and talk in detail on those. The first one was an innovation in a process. Engine valves is one of our products. In fact, we are the fastest growing engine valve maker, and I think now number 2 engine valve maker in India. when I joined 5 years back, we were probably number 5. And one of the reasons is the kind of initiative we put in innovation, both in product and process. So it started with product innovation. We saw the future. Engine valves are solid engine valves. I don't think I show, yeah. So I show a hollow engine valve, that's the future. We said that the future would be lightweight engine valves and high temperature engine valves. So lightweight, one of the things we said was to make it a little bit hollow. Now, to make it hollow, you need to drill a deep hole, fairly deep hole in a very narrow part. The stem of the valve that you see, the vertical section, is a maximum of 4 millimeters there. And the hole you drill has a diameter of 2 mm, and it has to be so straight that it doesn't introduce any lateral stresses while in operation. So drilling is not a difficult technology, but deep hole drilling of such a narrow hole, also wasn't so difficult when I told my guys that we should do that. But when they started doing this, there was a lot of failures, breakages. So what we were missing was an analysis of the new process before we actually tried the new process. So in this case, what we did was, we then went to a world-class institute, Fraunhofer Institute of Technology, and together we did a project. It was their role to do a design analysis of the new process. So it was all done on virtual engineering. There was no prototyping, there was no making of tools and machines before it was validated on computer. So that was an expertise we didn't have. I searched for universities in India that could do that. We didn't have that. Surprising. But these guys, to make the story short, they gave us a 6-month timeline, and they did it in 6 months, not a day more. And they gave the detailed plan to us on day 1, executed it brilliantly well. That's something we are missing in our company, and I'm sure in most of the Indian companies. It's called program management. So then we had a focus mostly on the process, tool, and design, but all virtual designs. And when it was proven virtually that you could do that, that's when we made the first prototypes, and all 150 of them were tested and passed. The next step we did was to make a valve that would go higher temperatures. These valves typically stay about 400 to 700 degrees, not more. But with engines becoming smaller and smaller, and with turbocharging and boosting, the combustion temperatures are higher and higher. So we needed either the same materials that could be cooled faster, or new materials which are expensive that can stand higher heat. So we went for the first one. Same materials, because cost is a prime concern for all customers. So we didn't change the design of the material. We said we'll fill them with sodium. Not a new technology, it's a known concept. So that was the second focus. Filling it sodium is not such a complex job, but once you fill it, to plug the hole at the top or at the bottom of the valve, which is about 2 mm, plug it with a 2 mm little plug and weld it. Weld a circumference of about 2 mm diameter, a circle of about 2 mm diameter, quickly in less than a second. That was a challenge. So we experimented with laser welding, also at Fraunhofer Institute. That's what is shown up there. And it was proven. So we have now, I think we are probably one company which have the ability to plug weld drill either from the top or the bottom, and plug weld either by laser or by friction welding. All this, the ideas were created in-house, but the expertise we sourced from outside. And at the end of the 6-month project, this was successfully launched into production. We are selling these to Chrysler now in US. So that's a success story. I would like to talk about. Next few slides, I'll talk what went behind this success. This is one example. Another example of manufacturing and innovation was gears. Gears are typically, we make transmission gears for two-wheelers, complete assembly. And they're made by forging a blank into a near net shape, and then a lot of machining to remove the material to the finer tolerances. Here also, it's driven primarily by cost because the design is not ours. Design belongs to the customer. Now, to reduce any cost here, we had to think of saving all the materials that we are cutting. If we can afford not to cut away the material, somehow forge it to a near net shape, we will save that 10 to 15 material that we are just machining it away. So the idea was also from inside of Varroc that can we form it to the final shape instead of hobbing, which is a material removal process. Again, the process design, the tool design, die design was all done by Fraunhofer here, again all on computer. And once it was validated, this is an axial forming process, so you have a upper and lower tool, and the die is a negative of the gear that we want, compensated for some allowance given to compensate for flow, but it's really a negative of the die, and then the process is just a high frequency forming in one direction, that is uniaxial. So it's a high frequency, that means it will press and release, press and release, press and release, at very high frequency. And we had given a cycle time equal to the hobbing process that we had, 17 seconds. So in 17 seconds, it can high frequency form a gear. The technology was proven on several gears, several complicated shapes, one with kidney holes also. But this one is an example of a project that was a partial success, and I'll also explain why. So the technology was developed, but the project was shelved. That's why I call it a partial success. We didn't productionize so far. This one took 2 years. The previous one took 6 months. The next example is on a simpler process, molding, polymer molding. This is driven by reduced rejections. Now we have a molding assembly, which is a center console of a car, that is the armrest panel in the front seat, between the front seats. There are several polymer molds we make, and the final assembly is done to make the final product in-house. So there's 15 different moldings. I've only shown 3 as example, but all those 15 moldings are done, and then it waits as work in progress before the final assembly. Final assembly is done, inspection is done, and shipped to customer. That's a very simplistic process flow diagram. The problem here was very high rejections and very high work in process inventory. So it was holding up a lot of cash here. Now, mind you, this is a very high volume business. We are making something like 150,000 assemblies a day. So it's, you can't afford to stop the line even for a few minutes. That will be production loss. So the focus was always on production, and we were losing a lot in terms of high inventory and work in process and high rejections. So we said, let's reduce the work in process inventory as step 1. And when we thought about it, we said we will have to re-engineer the process and then apply some traceability so that we know where inventory is being created, and we can monitor and track those. So the focus was on introducing a manufacturing execution system here, and to re-engineer the manufacturing process before we put the new system in place, and then introduce barcoding as a first step. And of course, we had to retrain or restaff the workers who are operating this. Those were the few focus areas. Unfortunately, during implementation, re-engineering was, although it was planned, it was not implemented because the plant management thought there were too high costs. Barcoding was done at the final inspection and not at the molding steps. So ideally, in our re-engineered process, barcoding should have been done in molding 1, molding 2, molding 3, and all 15 stations, so that you are tracking the work in process inventory created, and you run the final assembly with no work in process inventory. That was the initial intent. But because the project cost was high, the project was included the hardware, the mechatronics hardware, the software, and the implementation cost. It ran into 2.5 crores for a plant of about 200 crores within a budget year. That was found to be too expensive by the management. So what they said was, okay, let's do barcoding at the final station only. So we didn't re-engineer the process. Instead, we implemented the barcoding on an existing process. And since it was an existing process, we did not think the staff had to be trained enough on that. Now, the result of all this was that the work in process inventory continues to be at the same level, and the rejections continues to be at the same level, because rejections are created at the molding 1, 2, 3, and mostly in handling before the final assembly. Nothing changed. We spent about 40 lakhs in this one. And this is a project I call a failure. And I'll now next come to the summary of all these three. As a hindsight, if we had just looked at how much we are losing in bad products and work in process inventory, that was roughly about 1.2 crores a year. We thought 2.5 crores cost was too much. So we continue to lose 1.2 crores a year on that 200 crore revenue. The plant has grown to 300 crores, so the rejections are now higher. So that's on hindsight. This is why I call it a failure. To summarize all these three, I'd like to dwell on this one. The first one, we had complete management buy-in before we started the project. The management thought that this is a good project. Why? Because there was a customer pull. Customer was asking for lightweight products. And in this case, there was an RFQ from Chrysler for hollow valves. So they had no option. That's why the buy-in came in. There was a business need. We partnered the best in the world for developing the technology. The business put dedicated resources. They're not, temporary resources from another project. So they were dedicated and trained for this one. So because they are trained, at SOP there's complete compliance to the SOP evolved. So that's why we call this a success. The second one, the gear forming project. The buy-in part, there were 3 business heads during the 2 years this project went. So it took more time convincing the next business head that this is a project of importance. So eventually I conclude that there was no serious buy-in from the successor. There was no apparent customer pull. There was a business need because we had to make our products cheaper, but there was no apparent customer pull. Customer was not asking for a excuse me. Customer was not asking for an axial forming process. They were just asking for a cheaper gear. So while it fulfilled the customer requirement of a cheaper gear, because the customer did not ask for axial forming, there was no buy-in for this. Although we partnered the best partner in the world for this one, there was no dedicated resources because of no buying in, and there was no training completed for these guys. So that's why I say partial. The technology was developed because of the partner, but there's no implementation to production because of management buy-in. It's, I think, a very common story across all failures we've had so far. The last one is the manufacturing execution on a molding line, and the what we call just the bar coding project. This again, there were changes in the plant head, so there was no serious buy-in by the successors. There was a business need and there was a customer pull in this case, but the budget cut is what impacted everything and compromised on the initial scope of work here. And hence, no dedicated resources, instability in the workforce, process redesign was not done prior to the digitization. So while process redesign was done, it was not implemented. And so this I call a total failure. This is something one should never do. If you know that a process has to be re-engineered before implementation, if there's no budget for it, you would rather not do the project. That's the learning from this one, so it's completely red. There are several projects we did. It is not just based on these three. I think there are about 30 or 40 such projects, and I can classify into these 3 categories. As a result of it, what we said was, to achieve excellence, we need to follow a certain sequence. And so we built a manufacturing excellence roadmap. On the vertical axis, we have technology complexity. or the complexity of the application of technology. And on the horizontal line, we basically have a sequence. So the first one I call individual skills. You first need those, and I've categorized them also: basic industrial engineering practices, basic manufacturing engineering practices, system engineering, process automation. This is not application of electronics, mind you. Process automation is, I would probably call it minus the electronics. And then manufacturing systems. These are what one should have in your R&D group in manufacturing. Before you attempt the next one, that is application of electronics. So the first one is, if you have all of those in your R&D group, you are probably excellent at Industry 2.0 level. The next is use of electronics and IT, that's Industry 3.0. This is where you apply electronics to process and automation, use of data acquisition, use of process controls, all the PLC that we talk about is this. Virtual design tools. So this use of IT comes next. The third one is, once you are good at this, which is Industry 3.0, you start to then realize more value by collaborating across either functions or supply stream, value stream. So this is where manufacturing execution systems come in place, product data management, so part of PLM, and then collaboration either with the customer or supply chain. That's the next one. This requires connected systems. You could have these connected systems within a local area network, need not be internet. Then the next in line is use of internets or larger area networks, wider area networks. Data acquisition from legacy machines is by itself a technology that's developed. Complete factory automation, including new processes like 3D printing. And the last one is what we call big data. It's not data analytics, it's big data analytics. So big data means data that has videos and movies, so really large number of bytes, mega and terabytes of data. Augmented reality and artificial intelligence. So that is the sequence which we think we should use in order to squeeze out the maximum from these investments. Now, also let's take a look at where is the world on this one. As you go from left to right, the cost of manufacturing actually goes up. But then the value add also should go up. If the value add doesn't go up, you shouldn't attempt those. If I take the case of Germany, in history, the first, Industry 2.0 was complete in the early parts of the century, and they made the best. I'm just taking Germany as an example. There's also US ahead of that at that time. But I'm just taking Germany because it's still focused in manufacturing. US seem to have gotten out of manufacturing. So early 1900s, I think they mastered the first set, that is Industry 2.0. In the 70s and 80s, they mastered 3.0, that's use of electronics and IT. 90s and 2000 is the collaboration part. That's all the PLM that we hear from big companies like Bosch and Siemens. And then now, this last decade or last few years, we hear talk about the Industry 4.0, which is digitization or augmented reality and artificial intelligence. This is okay because they're adept at 1, 2, and 3, and are talking about 4. That's the right sequence, and also it's relevant for their industry because their labor is extremely expensive and few. They're not producing any more labor. I think it's easier for them to produce machines. For us, I think it's easier to produce labor, so we may have to follow a different curve. As you can see in the first Industry 2.0, up to 2.0, there was almost a 30-40 year gap. That's history, but over the years we have managed to narrow some of that. At least we are talking about industry application of 2 and 3. There are enough case studies in the industry today. 4, we are just talking about it. So more important than this is, is to look at where are we in India today. So if I take a snapshot on this roadmap for India, This is how it fares. Excuse me. So the blue ones are the ones where we think we are prepared or we are ready. The yellow ones are the ones where we think we have some work to do, and the red ones we are clearly not prepared. So if you see the individual skill set that is in a R&D group that you have, a manufacturing R&D group, we lack system engineering. That means how to piece the smaller pieces of the puzzle into the larger picture. This is in a lean engineering language, balancing the line. You may optimize a station, but if you have not balanced with another station, you create work in process inventory. That's a waste. So you look at the larger picture and try to design the system first before getting into the subsystem design. The process engineering is a subsystem design. Systems. I do not know of too many companies in India that have a documented manufacturing system manual. It takes some years of expertise to start writing this, and just the fact that we don't have written manufacturing system manuals means that we have more to go. The use of IT, luckily, we are pretty prepared, primarily because this is an entirely different industry doing that. This is IT industry. These skill sets, the virtual design, the PLC and data acquisition are not provided within this industry of manufacturing. They come as a service by the IT industry. So the IT industry seems to be prepared well before the manufacturing industry is. So collaboration between these is what you've seen in the last 2 decades to enable us to get into Industry 3.0, which is all this automation and use of IT. The collaboration part also, you see the IT companies trying to push through some softwares for collaboration. But here I put it yellow because, for a simple reason, collaboration means one party cannot implement the entire solution. It has to discuss with the manufacturing industry on a whole system before implementation. Now, if the manufacturing industry is not ready with system engineering and manufacturing systems, no matter how mature your software is, that connect will never happen between, and you will never get your optimal manufacturing execution system or connectivity between the various stakeholders. This is our learning from some of the experiments we have tried. So I suggest that if you do a gap assessment and find that you don't have system engineering or manufacturing systems knowledge, please do not attempt a manufacturing execution system. More often than not, what is happening is the manufacturing company relies on the IT service provider to give them a manufacturing execution system. It works, but when you have to improve upon them, that's when it turns out to be very expensive. You will be at the mercy of the technology provider, that's IT service company. The next ones, if you see, data captured directly from machines is something we probably are doing. But if you're not ready with Industry 3.0, please do not attempt 4.0, because 4.0 requires 3 as a prerequisite. I've heard that can we skip this process of 3 before going to 4? We done? Sure, thanks. So the last slide is, I've kind of put a excellence toolkit. How do you attempt going through that sequence? Really depends on where you are. There are different tools for different baselines. On the left side, I have put the baseline measurement in terms of your process capability. You could do it in terms of PPMs or quality measures or productivity measures. They all end up being the same. So if you are, if your in-house rejection, so to say, is around that 1.5 sigma, which is an in-house rejection of 10 to the power 4 ppm, that means you are dependent on the right side. If you see, you're dependent on daily supervision to get the job done. So the next stage for you is to make sure you have a stable, disciplined, and trained labor. The next stage is not automation or Industry 4.0. Next stage is simply have more process control. That will take you from 10 to the power 4 ppm to 10 to the power 3 ppm. That's the 3 sigma. So 3 sigma, companies that are at 3 sigma are the ones that have a good manufacturing system in place and following them. Now, just by having a good manufacturing system and following them will not take you beyond 3 sigma. You need something different. And that's where process automation comes. So you require automation if you have to go from 3 sigma to above. That means you have to reduce your rejections, let's say from 10 to the power 3 to 10 to the power 2. But mind you, if you do not have stable and capable processes, please do not attempt automation. You will not see the benefits, as I told you in the last example. You will end up spending costs, you will not see the benefits, because the machines have to have a certain level of capability on the part of the process. And then the last one is, if you want to improve upon that further, you need to start looking at the design of the process. So maybe introduce smart manufacturing systems, maybe connect the system, you will most likely find that the bottleneck is not within your manufacturing, but maybe in the value stream outside of it, maybe your customer, maybe your supplier. So that's where you need to connect these guys, right? So this is a short summary. What you will find that as you go up the ladder, your productivity and quality improves, and your total costs should come down if you follow the right sequence. If it is done right, the total cost does come down. If it ain't done right, you will find you're spending costs, but you're not getting the benefits. What is also important about this is, if you're down here, it's very easy to see where your improvement areas are. But the moment you are already at 10 to the power 2 ppm, it's very difficult to see where to improve upon, right? So that's why it's more important that you follow the sequence. So to conclude, first is you have to understand your own baseline. And the tools you apply depends on that baseline. Understand also the customer requirement and business requirement. If your competition is not at that industry 4.0 level for the next 10 years, should you attempt it and make yourself more expensive is a simple business decision. So summarizing this, your appropriate manufacturing system, whether it's manual or automated or connected or smart, depends really on your baseline, your process capability, and the gaps that you see between yourself and the business environment, which is the competition. This is all I had to share. We can probably discuss more in the question and answer session. I thank you very much for your attention. I'm available for questions for the next 5 minutes, I guess.
Thank you, Dr. Damodaran. We can perhaps have questions for about 3-4 minutes. Floor is open for questions. Yeah.
Good morning, sir. Thank you for the lecture. Hope you are listening me.
I can hear you. I can't see you because of that bright light behind you. Okay, yeah, I can see you.
Yeah. See, my one question is, if you go back to your manufacturing excellence scale, can you open? Yeah. In this, where this like teamwork and collaboration between the departments and rigor in execution, that kind of human skills also, I feel it should get included somewhere.
Yeah, those are basic hygiene items. When you are all by yourself, teamwork has no relevance, right? But when you are working in a team, that's the first thing that should be there. It's a basic hygiene item. I've made this chart assuming they are there. If not there, you look at my last slide here. The bottommost, I call that situation chaos. So if you don't have that, there's utter chaos. I think you should fix those first. And they are the most important things. And this is a good question, because we tend to either ignore the importance of that part, or we just do not address them, even if we know they're important.
Thank you.
Yeah. Good morning, sir. On your left side corner, it's Tabriz from Toyota Kirloskar.
Morning.
Thank you very much for sharing the failures, which I think very important for everybody. My question is on this manufacturing excellence toolkit that you tried to talk about. I was very much impressed when you said there is no point to go to Industry 4.0 without 3.0 being addressed. And the point that stable and capable processes are very important makes a lot of sense. Having said that, if we achieve stable and capable processes to graduate to the next level, what should be the first step is what is my question.
Yeah, I think you should understand always where the bottleneck is. Like initially you are focused in manufacturing. When you clean up manufacturing, then you will find that the bottleneck is in the parts coming in. So then you clean up the supply chain. Then we clean up the supply chain, you find that the bottleneck is in the schedule variation from the customer. So then you connect them and clean up that. So always when you, it's just like a manufacturing line, you know, you have a bottleneck station all the time if it's not 100% balanced. When you resolve that, another step becomes a bottleneck. Then you resolve that, another becomes. So this is like that, right? So you have to understand in your entire value stream, where's your bottleneck? That always is the next step. So if you are already at 3 and your processes are capable, the next question that should be asked is, how far is your competition away from you? The second question is, should you attempt Industry 4.0? What is the ROI on that? Once you have these 2 answers, a simple business decision, yes or no. If you are too far away from the competition, that means you're years ahead of the competition, right? You should just prepare yourself for the next technology, but need not implement it. It's a business decision, not very logical, but it's a right business decision, because in business, you always try to milk as much from the investments you have already done before investing in the next one.
Thank you, sir. Thank you very much.
Thank you, Dr. Ravi Damodaran, for a wonderful exposure in a simple, elucid way, how you can achieve manufacturing. Thank you so much. We close the session now.
Thank you, sir, and thank you, Mr. Umesh. A small memento on behalf of all of us. Thank you very much, sir.